Okay, any questions about anything? Okay, the crowd is shrinking a little bit as we, hello, yes?
Can we turn the homework in person, or is it only on Canvas this week?
Ask that question one more time.
So can we still turn the homework in person, or do you only want it on Canvas?
No, you can turn it in person as well. That's easy. Yeah, that's fine. In person or Canvas PDF upload. That's what we're experimenting with now, so that we don't have the email flurry between you, me, and the TAs. Any other questions? Okay. All right, I want to wrap up the kind of chapter 3 stuff today and move on into the kind of chapter 4 stuff. So remember what we talked about last time? We talked at some length about music, etc. Okay, and so music is something that is not like a sinusoid or a superposition of sinusoids. It's essentially a superposition of finite duration sinusoids that are of different frequencies and sometimes superimposed on each other, etc. So music is not pure sinusoid, pure sinusoidal, or even a sum of these, but it does certainly intuitively have frequency content. You think about it, you say, I'm hearing this note for a little while, or this superposition of notes for a little while, and the way you represent that in terms of diagrams and stuff, you can't just draw a little spectrum with arrows because it's not a superposition of sinusoids. So you represent that using a time frequency plot. So you represent this sort of quote-unquote time varying frequency content using a time frequency plot, as they call it. And sheet music is pretty much the most rudimentary example of such a thing. And the tool that people use in real life to analyze all kinds of different signals, not just music and everything, are things called spectrograms, which are essentially a technical generalization or whatever of sheet music, but there's a lot of complication to it. So this is a rudimentary example of a spectrogram. And one thing I didn't do last time, I didn't really draw, like, here's the spectrogram of what a scale spectrogram would look like versus what a chord spectrogram would look like. But let me do that now. And then I want to do one more thing about this, and then we'll move on to the sampling stuff. So, for example, suppose you had a scale. And let's make it an ascending scale. Didn't bring the keyboard with me, but you know how it goes, da, 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 you know, major scale, for example. So you have time on the horizontal axis, and you have frequency on the vertical axis. And what you have in the right half, the upper right quadrant, is a grayscale kind of image kind of thing, right? And you have darker where at that time that frequency is going. And it's darker depending on the amplitude or the volume or whatever you want to call it. So say I'm playing a scale, and I start off, say, at this frequency. So I'm going to have the spectrogram is going to look kind of like that for a while, and then it's going to look like kind of like this for a while, and then it's going to look kind of like this for a while, and there's going to be some blurring and overlap and everything, and then it's going to go like this. It's going to just not quite as much. I'll show you what I'm doing here in a second, and then it's going to go like this for a while. So this is the spectrogram of a major scale, the beginning of a major scale. So this is the quote-unquote beginning of a, say, C major scale. And the reason these things are the way they are is this is going to be f0. This is going to be f0 times the 6th root of 2. This is going to be f0 times the cube root of 2. Or no, it's 6th root of 2 times the 12th root of 2 is 2 to the 1/12 cubed is 2 to the 1/4. So it's the 4th root of 2. And then this one is going to be only 2 to the 1/12 times this. So this is going to be, this is what? I should have just done it with 2 to the 1/12. So this is f0. This is 2 to the 1/6 f0. And 2 to the 2/6 f0. And 2 to the, this is 2 6s 4/12, 2 to the 5/12 f0. And this is 2 to the, and there's going to be 2 more 12s, 7/12 f0. So that's the G. So this is going to be C, D, E, F, G. Those are the frequencies. And f0 is going to be the frequency of a C, which is going to be pinned down by the A440 to like 2 to the minus however many 12s times 440. And this is what the spectrogram is going to look like. And there's going to be all kinds of artifacts, and it's going to be thicker. It's not going to be quite exactly, you know, and there might be whatever harmonics, like there might be a little bit of stuff up here, you know, over those. But that's kind of what the spectrum of a scale is going to look like. And a spectrogram of a chord, say, this would be of a chord, say, for example, a C major triad. That's just going to be, that's going to look something like this. It's going to have a C, and it's going to have an E, and it's going to have a G. So this is a C, E, G, and they're all going to be happening at the same time. All right. So that's what spectrograms kind of look like. You know, they give you an idea of what frequencies are happening when. And the moral of the story is things can have frequency content without being pure sinusoids. They can be finite duration sinusoids or superpositions thereof, varying over time in frequency. Now, playing a piano, you have these discrete different frequencies for the different notes, but you can imagine having a signal whose frequency content varies in time, but in a kind of a continuous fashion. Okay, and that's the last thing I want to talk about from chapter 3, and that's something called, an example of that would be an FM signal. So here's one final example. Frequency content, I guess I'll put an underscore there, type. The example is what we call an FM signal. All right, so this is something, this is a signal whose frequency doesn't vary in discrete jumps, but continuously over time. So essentially, what you're talking about is a pure sinusoid, quote unquote, I'll put that in quotes, whose quote unquote frequency varies continuously in time. So mathematically, we're talking about something like this. X of t is equal to, say, a cosine of psi of t, where psi of t is just some function of t. So it's a cosine, has constant amplitude, and its frequency looks like psi of t. Now, what are some examples of the psis that we might encounter? Okay, so here's an example. And this, I always forget that this particular shirt is really annoying because the sleeves just come down and they get all covered with chalk. I'm erasing the board. And the left sleeve comes down more because as someone who played tennis for many years, my right forearm is much bigger than my left forearm, so that holds the sleeve up. But anyway, but I like the shirt too much not to wear it. So what do you do? What do you do? Okay. All right, so an example, psi of t. How about psi of t is equal to 2 pi f0t plus phi. That's a perfectly good psi of t, but wait, oh, that's just a familiar thing now. Then x of t is just a plain old sinusoid of constant frequency and amplitude a. This is just a pure sinusoid, our old friend that we've been dealing with all this time. All right, so this psi of t is linear or affine, technically, in t. What if we add like one more term, say? How about, and I always forget whether I want to put a 2 in front of the mu. So how about psi of t equals 2 pi mu t squared plus 2 pi f0t plus phi. Is that what I want? Yeah. That's like one level up in complication from this. If mu is positive, so note, if mu is positive, this psi of t is increasing in t quadratically. All right. Now, what is the signal A cosine of that going to look like? So for this psi of t, x of t looks roughly like this. It's going to be a cosine whose frequency increases like so. See, it's getting whatever. It starts off slow variation, and this of course is a and minus a. And it increases because the psi of t is increasing in t, it looks like that. Now, in general, the psi of t you put in there is not going to be strictly increasing or strictly decreasing. It's going to be time varying. It's going to go up and down, up and down, up and down. So what will happen is the signal x of t will look kind of like this. So for, see, left sleeve comes down. So for general psi of t, we have x of t looking like something like this. It's going to go, slow for a while, then fast for a while, then slow for a while, and then really fast for a while, like so, and slow, that kind of thing. And this is all supposed to be amplitude A. And this always reminds me of a toy that we had when I was a kid. I don't know if you guys still have it. I know it's in the Rochester Toy Hall of Fame. Anyone ever heard of a Slinky? Okay, I didn't know if it was still a thing. Okay, so it's kind of like a Slinky. So it's Slinky-ish, Slinky-esque. How about that? All right. Now, there is something we can say about these signals. And by the way, this is the kind of signal that's flying around in FM radio, right? Like in FM radio, you have a really high frequency cosine, and the numbers on the FM radio dial, like 90, 95.5, 102.7, those kind of numbers, those are megahertz. So you have a frequency, a megahertz frequency sinusoid whose frequency is modulated by the music, okay? So that's what's going around in FM radio. And the reason FM has better sound quality is because the high frequency thing passes even better, less attenuated through the atmosphere, et cetera, et cetera, et cetera. But anyway, for one of these signals, for an FM signal of this kind, okay, what we call the instantaneous frequency at any time, say of x of t, at time t1 to be, we define this to be the derivative of psi of t with respect to t at time t1. So it's d psi dt evaluated at t equals t1. So if someone says, well, someone comes up to you in whole plaza with an FM signal expressed as x of t equals a cosine psi of t and says, I want to find the instantaneous frequency of this signal at time 17, say, for example. Well, what you have to do is you have to take d psi dt and evaluate it at t equals 17. So what about when psi of t is this linear or affine thing? So for psi of t equals 2 pi f0 t. Oh, I forgot there's a 1 over 2 pi here. 2 pi f0 t plus phi. That means that d psi dt is equal to f0. Good. This definition of instantaneous frequency works in the special case of a constant frequency sinusoid. That's the first thing we ought to check. What about for this signal with a quadratic, 2 pi mu t squared plus 2 pi f0 t plus phi? So for psi of t equals 2 pi mu t squared plus 2 pi f0 t plus phi, we have d psi dt is equal to 2 mu t plus f0. And this is linearly increasing in t. So the quote-unquote instantaneous frequency increases linearly in t. As we mentioned, it's not enough to have psi of t increasing linearly in t for the frequency to increase. You have to have d psi dt also positive. Now, a signal whose frequency, one of these FM signals whose frequency is monotonically, whose instantaneous frequency is monotonically increasing in t, has a name. So terminology, a signal whose instantaneous frequency, and this is an FM signal, so let's put that in there. Frequency psi of t, d psi dt, 1 over 2 pi d psi dt, is increasing in t, so increases monotonically in t, is called a chirp signal. And during the lab next week, which you're gonna have lab next week, and one of the things you're gonna do is generate a chirp signal using MATLAB. And why is it called a chirp signal? Well, think about like how some birds sound, like they go reet, reet, reet. I don't know. I'm not a good bird imitator. But anyway. Okay. So that's pretty much wraps up the material in chapter 3 of the book that we want to cover in class. Does anybody want to pause and digest and ask a question or two, or make a comment or 3 or whatever, or before we move on to the sampling stuff? Super important stuff coming up. Yeah. Yeah. Monotonically means, increasing monotonically means that it never decreases. That's just a math term. Yeah. Monotonically. Not monotonously, but yeah, that's same root structure, but I suppose you can think it's monotonous.
So it's never decreasing?
Yeah, yeah. Yeah, it's always increasing. Yeah.
I glanced at the lab handouts and there's like a bunch of pre-lab stuff. Should we do that out?
I think in the guidance, like the main handout for the lab, I say that it's a good idea to do some of those on your own, just to get your hands dirty on the stuff. But the thing with the lab, just lab as homework in this course, both things. I think of these as learning exercises rather than assessment exercises. So think of it more as I want to understand what's going on in this lab and do it and get checked off rather than I have to get this to work exactly right. Okay. So the TAs are going to be there to essentially check you off and make sure we're all on the same page, the lab stuff. And the Shazam thing, that's going to be a little different. That's going to stretch out over a period of weeks, and I haven't quite figured out how to organize that yet. But anyway, any other questions? Yeah.
So the Slinky-like function follows a sine or cosine model.
Sorry, say that one more time.
The Slinky-like function for psi follows a cosine or sine model. So we have a quadratic and a linear model, and so that was one.
Oh no, this will be for some general psi of t. Like for example, psi of t equal. It could be. You could have a psi of t be a cosine or a sine. I tried to draw this so it was kind of randomly happening rather than a periodic frequency. But sure, you could have it in there. But it could be like e to the minus 3t plus e to the 4t plus cosine of that kind of thing. It could be any function of t. Any other questions on this stuff? Okay. So now you've learned about spectra. You've learned about frequency domain representation of signals. And now we're going to talk about a really important thing, and that's the whole idea of sampling. Now, sampling and interpolation. And what we're going to do is I'm going to open up with an example where there's no math, just pictures, and then we're going to talk about the math of it. Okay, so the next, and all this material is in chapter 4, but it's super important. Everything is super important, so I'm not even going to say that. Is sampling, interpolation, and related ideas, so etc. Okay, so anyway, what the pictures I'm going to draw, like I said, I'm going to open this up with a non-math example, and first I'm going to tell you a story, of course, about when I was a kid. And it's this. My brother and I, my brother's only a year and a half younger than me. And he went to Cornell, actually. He was an applied engineering physics major at Cornell. But anyway, he and I used to get up early on the weekend, heaven knows why. And this is before Saturday morning cartoons came along. And we lived in New Jersey, of course. So, like the Homedale guy, where are you? Yeah. And Bergen County guy, where are you? Yeah, and of course Cedar Knolls. I saw you. Yeah, okay. These guys know what I'm talking about. Well, maybe they don't, because back then, TV. I mentioned this actually when I talked about the Hertz terminology. There were only limited number of stations, like 2, 4, 5, 7, 9, 11, and 13, and they were broadcast stations. And almost all of them on the weekend mornings had religious programs. Okay. Well, my brother and I weren't particularly interested in those. There was, however, one program that we watched religiously, okay, and that was called, get this, The Modern Farmer. Okay, now, if you Google on Modern Farmer, you will discover that there is a Korean thing, a Korean series called Modern Farmer. Okay, now, I don't know what that's about. I know Korean stuff is all the rage right now. I mean, whatever, Parasite won Best Picture, BTS is probably the most popular band in the world right now, so Korean stuff is everywhere. But this is not a Korean thing. I did find a nostalgia website that alluded to this show that I'm talking about. Only one, though. And I'll post that link so you can, I'm telling you the truth. Such a show existed. Okay, so what was the show about? Well, the show was literally about farming in the 1950s and 60s, right? And I learned all about fertilizer and, nitrogen, phosphorus, potassium, all that kind of thing, and there were videos of cows being like their stomachs have a door on the side so they could take the stuff out and look at it and see how the cows are digested. It was really gross that way, but they had these cool tractors, right, with big wheels on them, right, and the tractor would like lumber across the screen, but the wheel wouldn't do what it was supposed to do. Okay, now imagine, a 6-year-old, 7-year-old is looking at this TV. sees this tractor going across the screen, and the wheel goes, and then it goes backwards, and then it holds still, and then it goes forward, you know, really confusing to me. Okay, and I'm like, why is that? How can a wheel do that? That's like physically impossible. And right then, I decided that I had to study ECE and particularly signals to understand why this was happening. Okay, so let's look at that example, the modern farmer-inspired example of you're watching a movie, right? So let's first talk about an example from real life. And this is probably the first sampling thing you ever saw in your life is when you watched a movie, sampling and interpolation thing you watched. Okay, so we're going to talk about a standard Hollywood movie. Okay, so what is a movie? A movie is, first of all, something actually happens, and I'm not talking about a CGI animation thing, I'm talking about an actual live action film here. So let's be really specific about that. All right, so you start with a visual signal. Something's happening in the real world that people can see, and you film it, okay? And the filming is actually not a continuous thing, it's a bunch of samples. And so a standard Hollywood movie, what you've got is you've got a visual signal. Okay, let's call it X of t, and it's filmed. So this is filmed, and you get the movie signal. And the movie signal is actually going to be a sequence of still pictures of X of t. So it's going to be like X of n. All right. Now, what's happening when it's filmed? When the filming samples this visual signal X of t every how many seconds? Does anybody know off the top of their head? Yeah?
24 frames per second.
24 frames per second. So that means that this thing clicks along, sampling the signal every 1/24th of a second. Okay, so this samples X of t at every, or just say not at, samples X of t every 1/24th of a second. That's 24 frames per second. Okay, and we're going to have notation for ideal samplers with sampling interval t sub s, sampling frequency f sub s, but whatever. I just want to draw this schematically for now. Okay, now when the movie gets distributed and sent to theaters or goes direct to DVD or whatever, when you watch this movie, this is the video production part. When you watch the movie, what happens is that this movie signal X of n goes into your brain, so to speak, and I'll put brain in quotes because what I mean here is every part of your physiocognitive apparatus relevant to processing a visual signal. What comes out of your brain is some continuous time signal y of t. This is what you see. Okay, and you may say, well, wait, don't I see X of t? Well, when I was watching The Modern Farmer, I wasn't seeing X of t all the time. So let's look at that example. Look at the example of a wheel. So consider you're filming a rotating wheel. And if you want to, have it be a more fun example, think it's like some kind of James Bond car, some Aston Martin that's whizzing across the screen from left to right, and it has a wheel. And the wheel, so this rotating wheel has a radial marking. So you can sort of tell what orientation the wheel is by watching this radial marking. Okay. Now, suppose that, so think of the car going from left to right across the screen. So for example, car left to right across the screen. What does that mean? Well, which way do the wheels have to be going in real life? So when filmed, the wheels are rotating clockwise at some frequency, right? Because the car is going left or right across the streams. In real life, when they're filmed, the wheels are rotating clockwise. All right. Now, depending on what speed the car is going, what speed the wheels are rotating, different things can happen. So let's look at some cases. And I'm assuming here that it's a standard Hollywood film. So what's the first case? The wheel is rotating one rotation, exactly one rotation. So case one, wheel makes exactly one full rotation every 1/24 of a second. It just so happens to be going like that. And you may say, well, wait, does that make any sense on a wheel on a car? Well, let's think about it. Let's think about it. Say the circumference of the tire is 6 feet, right? Doing English units here. And making one rotation every 1/24 of a second means that that's 144 feet per second, right? Is how fast the car is moving if the wheel has circumference of 6 feet. How fast is that? That's about 100 miles an hour. So it makes sense, physical sense. That could happen in real life. Did anyone ever marvel at the fact, as I have my whole life, that miles per hour and feet per second are sort of the same kind of order of magnitude unit? 1.46 is the factor that relates miles per hour to feet per second. It's 5280 over 3600. Is that cool or not? That's great. OK, so what does the wheel look like? This is what the sequence of frames. The wheel, second frame, it makes exactly one rotation, and it gets strobed again at that spot. So that's what the radial marking looks like. So in some sense, it looks like the wheel is staying still, right? In other words, when you put this sequence of x of n's through your brain, you see a stationary wheel. So sequence of frames look like this, and they're processed by your brain into, quote unquote, wheel standing still. And indeed, if you watch a film like this, you'll see the wheel standing still. You'll see all the detail of the treads. You'll see that it's actually, a Michelin snow tire, like I have on my car, my new car. New last March, so it's not that new anymore. But anyway, OK. Next example, case 2. The wheel makes exactly 3/4 of a clockwise revolution every 1/24 of a second. And so it's going a little slower than the first case. And what does this mean? This is 18 clockwise revs per second. This one here is 24 clockwise revs per second. All right, so what does the sequence of frames look like in that case? It looks like this. Again, the left sleeve. So it starts like this. Then it makes 3/4 of a clockwise rev. So the next frame is here. Then it makes 3/4 of a clockwise rev. The next frame is down. 3/4 of a clockwise rev. Next one is here. And then 3/4 of a clockwise rev. It's back up top again, and so on. OK, Okay, so even though in real life, when filmed, the wheel is rotating clockwise, you see the sequence of frames where it goes dun, 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 dun. It looks, your brain is going to put that back together as, quote unquote, the wheel is going counterclockwise at like 1/4 of a frame, or 1/4 of a counterclockwise rev per second. So your brain does what? Brain processes this into, quote unquote, wheel rotating counterclockwise 1/4 of a rev per frame. Or, if you wish, 6 revs per second counterclockwise. That turns out to be the number that goes with that. And so, you know, if you sort of get the car out of your mind and just look at the wheel, that's what it looks like it's doing. But then you back off and you look at the whole scene and you're like the 6-year-old watching The Modern Farmer. You know, what's wrong with this picture? Car's going that way, the wheel's going that way. Okay. Next case. Next case, the wheel makes exactly 1/2 rev per frame. So 1/24 of a second. That's 12 revs clockwise per second. What happens then? Well, it looks like this. Now, how would you put that together? Well, if you look at the whole picture, you'll want to see the thing going around clockwise, but this is also compatible with counterclockwise revolution of that speed. And it turns out that your brain can't decide between those two. It flips back and forth. When you stare at something that's doing this, for a second you see it going I'm not a second exactly in technical time, but for a bit you see it going clockwise, and a bit you see it going counterclockwise, and you can't sort that out. And it's kind of like a Necker cube. Does anyone know what a Necker cube is? Okay, I'll show you. First, let me say that the brain can't decide. Your brain can't decide between clockwise at 12 revs per second and counterclockwise at 12 revs per second. So here's then an example of another brain can't decide thing. This is called a Necker cube. You just draw a cube, but you draw all the parts of it, like so. And now you stare at it. Okay, so which face of the cube is out of the board and which face is in the board? I can't even see it. Like, is this face the one that's out of the board and this face the one that's in the board? Or is it this face that's out of the board and this face is in the board? If you stare at that long enough, your brain just bops back and forth, okay? And you go insane. Actually, insane is probably not a PC word. So you become differently thinking. Okay. What do we do here? What do we call this? This is what I call the pesky boundary case. Now, Alex remembers this from 2 years ago or a year and a half ago, right? This case comes cropping up again and again and again as we go through the course. And so what we do is we always sort of push it off to the side and say, we'll deal with this later. And then when all is said and done, you will get a handout that explains this mathematically. But we really can't do a good mathematical explanation until we've done a lot more work. So let's call this the pesky boundary case and abbreviate that as PBK. That's the pesky boundary case, and we'll see this in the future. So we'll see further manifestations of this. All right, finally, case 4, the wheel makes 1/4 of a rev clockwise per 1/24 of a second, which is 6 revs per second clockwise. Then the sequence of frames looks like this. And if you look at those, you'll see it looks kind of clockwise. So your brain puts this back together correctly in a way that corresponds to reality. The reality that was happening when the thing was actually filmed. So your brain reassembles this quote unquote correctly. Okay, so we see that in 2 out of the 4 cases, your brain does something that's unequivocally wrong in the sense that it puts it back together into a way that it didn't happen in the real world. In one case, it puts it back together into what actually happened in the real world. And in one case, your brain is equivocal. It equivocates. Okay, so in terms of the XY pictures we drew above, so in terms of x of t going into this, giving you x of n, going into the other box and giving you y of t. So this is the film-ing, and this is the brain. Y of t is quote unquote correct only in case 4. It's wrong in cases 1 and 2, and in case 3, it's not even a thing. All right, so that's the example we want to put some mathematical life to, or shall we say, or you might think of it as killing the example with mathematics. But let's take the 3-minute break, and then we'll do that. Okay, so anyway, back to this. Let's talk. We have to go for a new box of chalk. Chalk varies in quality between boxes. And sometimes you start writing and it just flies into little pieces, and so you know you've got a bad box. But anyway, okay, so let's get technical about this stuff. Okay, and how do we do that? First, we're going to talk about ideal C to D conversion, or ideal sampling. And we have a notation for that. So x of t goes into some box, and out comes x of n. And what we're going to do is we're going to put like a ts here, like so. And the notation will vary a little bit, but this is the basic idea. You have this box, and you have a ts in here, and ts bigger than 0 is like a parameter of the box is given. And what is x of n? X of n is equal to x parentheses of n ts for all integers n. Okay. This is what we call an ideal T sub s sampler, or if you want to think frequency style, that's fine. F sub s sampler with sampling frequency 1 over Ts. That's Fs. So Fs is called the sampling frequency. And Ts is called the intersample interval, or sampling interval. All right. These things come up all the time. Like at the front end of any DSP system, like if you want to create a CD, like when we talked earlier in the semester, we had this on the board in some form or another, but you take the music signal, you sample it every 44,100, at a frequency of 44,100 hertz, and that's your X of N that you get out of sampling. And then you add up a whole bunch of bits to it to put it on a CD, whatever. Okay, so that's an ideal sampler. Now consider putting a sinusoid into this guy. So let's look and see what happens when x of t, and by the way, this is the whole motivation for Oppenheim, the guy who invented this bracket terminology for discrete time signals, to do brackets for discrete time and parentheses for continuous time. He wanted to write this. He wanted this to be a thing, and that's why the brackets. He wanted to be able to write the same x on both sides of the equation, but have it mean different things, because one of them is a discrete time signal, one of them is a continuous time signal. I used to like that, but then I kind of grew out of it. So anyway, see what happens when x of t is a cosine. So a cos 2 pi f0t plus phi. Okay. What is x of n? Well, you just plug in nts everywhere you see a little t, and you get the value of the sampled signal at time n. So then x of n is equal to a cosine 2 pi f0 nts plus phi. Okay. Now, depending on the relationship between f0 and ts and all that, that x of n is going to look different. But obviously, we threw away an awful lot of x of t to get this x of n, right? So note, to get x of n, you quote unquote throw away most of x of t. You only keep a discrete set of samples out of this continuum. You throw away the whole bunch of x of t in between the sampling instance. So a priori, we should not expect, okay, thus, we don't, I should say. I don't like to say should, because that's one of those compulsive kind of words, that we don't expect, on the face of it at least, for x of n to tell us what x of t was. So we don't expect x of n to, quote unquote, contain enough info to tell us what x of t was. In other words, what continuous time signal got sampled to give us this x of n. It's just a bunch of dots, and there's zillions of ways of connecting the dots. So in terms of like that a kid would understand, there's x of n is like a bunch of dots, and there's lots of ways to, quote unquote, connect them. Okay, now what about this connection process? Well, maybe I'll save that up. So there's no way we can tell what x of t was just from that sampled version x of n. But suppose someone tells us x of t was a pure sinusoid. So, but suppose someone says, suppose we know that x of t was a pure sinusoid when sampled. Okay. That's an additional piece of information that someone could tell us. Then can we figure out what x of t t was given x of n? How many people think so? How many people think if I sample a sinusoid at some frequency, fs, some sampling interval t sub s, I get a sequence of samples, that I can figure out what that sinusoid was given those samples?
If Ts is greater than T naught, or sorry, Fs is greater than F naught, then probably we can.
You're close. Okay. Why do you think it has to do with the relationship? Why do you think it has to do with the relationship between Fs and F0?
I guess it'll.
Don't use anybody's name when you give me this.
I don't know. Okay.
Okay.
I mean, empirically speaking, if we have enough dots that are closer than, I mean, supposedly just two endpoints on a wave.
Yeah.
If we have more dots between the two endpoints, we should be able to figure out the shape of the wave.
Yeah, that intuitively that's correct. Okay, but it is deeper than that. But you're right that it turns out that sometimes yes, sometimes no. Like you might need a little more information. We might need to know, for example, that x of t was a sinusoid whose frequency lay in the following range. We might need to know something like that. Okay, but the answer to this question, raw, okay, this question stated the way it is now is no. Well, it's not a question. Can we then, let me pose the question, can we then determine x of t from x of n? No, in general. And here's why. Okay, I want to consider a whole bunch of sinusoids, all of which lead to the same sequence of samples when sampled at frequency f sub s. Okay, so suppose, say, x of t were something like a cos 2 pi f0 t plus phi. That's what we're kind of supposing here. Then, for any k bigger than 0, the signal, let's call it q of t. Q of t equals a cosine 2 pi f0 plus k f s t plus phi. That signal, I claim, gives rise to the same samples as the signal x of t did. Why? Let's see what happens there. So it gives rise to the same x of n. That is to say, so when t sub s sampled, that is to say, q of nts equals x of nts equals x bracket n for all n. All right, why is that the case? Just do the math. Q of n equals q of nts. Well, let's just say q of nts. Let's not even say q of n. Q of nts equals a cos 2 pi f0t plus 2 pi k fs, back off, 2 pi f0 plus k fs times nts plus phi equals a cos 2 pi f0 nts plus phi plus 2 pi k n fsts. What is FSTS? 1. Everyone sounds so tentative. FSTS is 1, so this is a cosine 2 pi f0 nts plus phi plus 2 pi kn. And when you add an integer multiple of 2 pi to the argument of a cosine, that doesn't change it. So this is the same as a cos 2 pi f0 nts plus phi, and that's x of n, which is what we wanted to show. Now, this signal q of t, when k is not 0, and here I'm assuming k is positive, is not the same signal as x of t. I want to emphasize that. It's a much higher frequency cosine for large k. Okay, this is the wrong eraser. But it, quote unquote, fs samples the same as x of t does. So this q of t, these signals, q of t, there's a different one for each positive value of k, are different from x of t, but, quote unquote, f sub s sample, or if you wish, t sub s sample. I'm going to use those kinds of phrases interchangeably, the same as x of t. All right, so there's lots of different even pure sinusoids that give rise to the same sample as x of t. That's always going to be the case. Now, what do we call these q of t's? Terminology. And this is something that I use, terminology I use, that the book doesn't use. And this is the first instance over the course of the semester where I'm going to be using terminology that the book doesn't use. And every time I do that, I'm going to warn you, okay? I'm going to warn you that I'm not doing that. So be warned. So this is not in the book. Each of these x of t, each of these q of t's, I should say, so all these q of t signals are called continuous time aliases of x of t with respect to, does everyone know WRT means with respect to? Have you seen that in life? You read anything by David Foster Wallace? Anybody? Yeah? So you've seen that a lot. Yeah, WRT with respect to sampling frequency f sub s and alternatively, sometimes we'll say with respect to sampling interval t sub s, whatever, same thing. We call those things continuous time aliases of x of t with respect to the sampling frequency f sub s. All right. So now let's go back to Hope Plaza and say someone comes up to you in Hope Plaza and asks you the following question. You know, here's a sinusoid, like a cosine 2 pi 440t plus pi over 3, say. And they say, what are the continuous time aliases of this signal? What would you say?
Depends on the f of s.
Yeah, you could say that, or you could say, you know, you're asking me a stupid question, or you're asking me, you're not really asking me a question that I can answer. And if you were Buddhist, you would just remain silent. You would just. Why? Because if you have a sinusoid, the expression continuous time alias of that sinusoid makes no sense unless you say what sampling frequency it's a continuous time alias of that sinusoid with respect to. You need both. You need the sampling frequency. And that's why it's part of the definition. Now, why do they call them aliases? Why the name? Well, alias is one word, one use of the word alias in real life is a fake name for something, right? Like somebody assumes an alias. Like, you know, Samuel Langhorne Clemens, right? Had Mark Twain was like an alias for him. And O. Henry was William Sidney Porter, and Charles Lutwidge Dodgson was Lewis Carroll, and there's all kinds of people like that, right? George Eliot was a woman. That was her alias. You could go on and on. But that's why the name, you think of each of these aliases each of these continuous time aliases of x sub t with respect to the sampling frequency f sub s as quote-unquote masquerading or posing or assuming the name of masquerading as or assuming the name of x of t under f sub s sampling. So like if one of these q of t's came up to the true x of t before it got to go into the sampler and knocked out the true x of t and went in the sampler instead, then the recipient of those samples would blithely go along thinking that x of t got sampled, but really what was happening was this bad continuous time alias was getting sampled. All right. So that's why we call them continuous time aliases. Now, this argument here demonstrates that because you can do this for any k bigger than 0, there are continuous time aliases of x of t of arbitrarily high frequency. Okay, note. Take k in the above argument bigger means that you can deduce that there are continuous time aliases of x of t with respect to, always remember, that's part of the definition, with respect to f of s of arbitrarily high frequencies. So f0, f0 plus fs, f0 plus 2fs, etc. All those guys, you're going to have a continuous time alias of x of t with respect to fs of each of those possible frequencies. OK, so you may say, well, what about going the other way? Like, can we find like a continuous time alias of x of t that has a lowest frequency? And the answer is yes, indeed, we can. Now, how would you do that? Well, in the discussion so far, I have restricted the k thing to be bigger than 0. But you don't have to do that. You could subtract off f sub s from f0. So it turns out, on the other hand, that there is, and we're going to have to assume, by the way, that, and here's our next manifestation of the pesky boundary case, there's a continuous time alias of x of t with respect to sampling frequency f sub s of smallest frequency. Okay? And we call that the principal continuous time alias of x of t with respect to f sub s. Call this x sub prin of t, the principal continuous time alias of x of t with respect to x f sub s. How do we find it? Well, I'm going to draw. Mathematically, equation-wise, what we do is note that if we take x of t, or if we take a cosine 2 pi f0 minus fs t plus phi, that sample's the same as x of t. So if I call this one q of t, and in fact, q of t equals a cosine 2 pi f0 minus kfs t plus phi. All these, so this is for all k bigger than 0, satisfy so let's put n in fact, satisfy q of nts equals x of nts equals x of n. So the point is that I can subtract multiples of f sub s from f0, and I still get a signal that samples the same at frequency f sub s as x of t does. But it's our custom always to talk about these sinusoids with positive frequency. And obviously what happens if you take k big enough here, if you take k big enough, the quote-unquote frequency thing in here is going to go negative. But that turns out to be undoable by the fact that cosine of minus theta is the same as cosine of theta, so you just flip that around, negate the theta, and you get something with a positive frequency. So let's describe the process, and we might not,
Is it for all k greater than 0 or all integers k?
Yeah, all integers k bigger than 0, correct. All right, so find x prin of t as follows. And I'm going to have to review this next time, so maybe you want to just sort of sit back and stare for the moment rather than take notes. This is f space. This is 0. And say here's f0. And suppose fs is, say, here. So fs is here. So let's say fs over 2 is here. And minus fs over 2 is here. Now, it turns out that under very general circumstances, if I step f0 down by multiples of f sub s, so you step fs or f0 down by multiples of fs, integer, you're going to end up eventually landing at exactly one frequency that lies strictly in between plus and minus fs over 2. So you land eventually in the open interval minus fs over 2 up to fs over 2, except when what? Sometimes you don't land in that open interval. What might happen? Yeah.
Too big of a step.
Well, you'll always, you can't step completely over that because you're only going by lengths of fs. But, yeah.
You could land on fs over 2.
Yeah, you could land first on this and then on this. That's a bad scene, okay? So we want to avoid that. And that turns out to be this computation's version of the pesky boundary case. So this is provided not the pesky boundary case. All right, so you land in there, and it turns out that either plus or minus where you land is going to be the frequency of the principal continuous time alias, and it's always going to have the same phase, but possibly with a minus sign. And we'll figure that out next time.